Okay, the last thing I want to do is sort of package all of this information into a very nice function. So what we want to do in this last little section, we're going to write a function called middle k interval. It's going to take the following arguments: mu, which is going to be the mean of the normal random variable from which we're supposedly sampling; sigma, which will be the standard deviation of the normal random variable from which we sample; n is the sample size we're going to select; and k is going to be the middle percentage written as a decimal for the interval we want. What we're going to do is this function is going to return the middle k interval with the specifications as above. So essentially, if we go back to example 2, you'll notice this is the n parameter we would input. This would be mu. This would be sigma. And our k, we would change this to a decimal. We would put 0.99. And it would go through all of these steps and essentially return this particular interval. Okay? I'm also going to show you the print and paste functions, which will help you kind of package an output a little bit nicer. Feel free to use it in the future, but you don't have to. Okay? All right, so let's set this up. We want middle k interval. This is going to be a function. And in addition to setting our in addition to setting our arguments, I'm gonna standardize or sort of put default values for each one of them. So for mu, I'm gonna put a default value of 0. For sigma, I'm gonna put a default value of 1. For n, I'm gonna put a default value of 1. And for k, I'm gonna do a default value of 0.95. Okay? Now remember, we open up our squirrely braces or curly braces, and we're gonna put the function or the content of our function inside here. So we can follow the same basic steps. So let me scroll back up and to where we wrote down our margin of error approaches steps. First, we determine the middle percentage. So this is coming in as a input, right? So this is coming in as an input of our function. From this, we create essentially alpha over 2, which is going to help us determine our critical value, z crit. Okay? Once we have our z critical, we're going to find the margin of error. Keep in mind that for our margin of error, the sigma and the n are also going to be inputs. And then finally, we're going to use this general form where 50, this is typically our mean. This will be an input. We'll have our margin of error computed, and we're going to try to return this particular interval. Okay? So we'll write out the steps. First, determine alpha, which is the missing probability in the tails. So alpha is going to be defined by 1 minus k. And again, it's very important here that k comes in as a percentage. Okay? So middle percentage written as a decimal. This is important. Otherwise, this 1 minus is going to give us trouble. Okay? So written as a decimal. This is very important. All right? Now we know that our critical value, the z-score, all right, our critical value, this z alpha over 2, we can compute this using our Q norm. We take 1 minus alpha over 2, and then we use the standard normal parameters of 0 and 1. So 0 is for the mean, 1 is for our standard deviation. So we're going to set z crit, oh, sorry, my Python is showing here. This should be the assignment operator backwards arrow. So z crit is going to be our Q norm, 1 minus alpha over 2, 0, 1. And now we can create our margin of error, which is going to be our z critical value times our input sigma divided by the square root of our input n. Does that make sense? So we now have our margin of error. Okay? So I'm going to create two variables. The lower bound is going to be for where my interval starts. So this would be mu minus margin of error. I'm going to create another variable called upper bound, which is going to be mu plus my margin of error. And now I'm going to show you how to return a statement that's going to put all of this stuff together. Okay, so we're going to use the print command. And now inside of print, I'm going to use a command called paste, which is going to take all of the arguments and paste it together as a single string, which will be our final output. All right, so I'm going to put in quotes a parentheses, then a comma, and now I want my lower bound. comma. Then I'm going to do a comma and a space, comma. So maybe I'll list them out like this. It'll be a little bit easier to see. So it's going to start with a parentheses, print the lower bound, then print a comma and a space. Then it's going to print the upper bound. And then it's going to print a close parentheses. Okay? So each one of these is going to, piece by piece, put the pieces together. All right? Maybe in a comment I can kind of show you what's going to happen. What I want is essentially, my number 5.3 comma 6.73 whatever end parentheses. But these are going to be coming from my variables, and this extra stuff like this open parentheses, this space with the comma, and this other parentheses needs to be inside of quotes because I'm going to glue all of this stuff together into a text piece of text. Okay, so let's run this function. Everything seemed to work. And now let's test it out. We'll do middle k interval, and let's use it on our example too. So let me try to remind myself. We had a k of 99, we had an we had a mean of 50, a standard deviation of 10, and a sample size of 35. Okay, so our mean here was 50, our sigma was 10, our sample size was 35, and the k value we wanted was 0.99. So let's see if we run this, if we get the same interval. All right, so notice it prints back in a very nice interval form. We have 46.646 and 54.934. This was exactly our answer from up here. All right, and it's been pasted together using the paste. Right, so this paste command created this expression as a text, and then print sent it back out to the console. All right, so this is where we have our nice middle k interval function, which will be helpful. There is a prepackaged R command that does all this for us, so don't worry too much about memorizing this particular thing, but it is a nice exercise in writing R functions and making things customizable. Okay, we can try, let's just do another one. All right, using this middle k interval. Another thing we can do if we want is we can actually use the round function. So suppose I only want to round, I want my lower and upper intervals, my lower bound and my upper bounds to be rounded to 3 decimal places here. So I can do something like this. I can add the round function in the low bound, the upper bound part. And now if I rerun this, you see that it rounds it to 3 decimal places. A couple of things you may notice here as our middle percentage increases, right? So the part in the middle that we want increases. You'll notice that the interval itself gets wider, and this should kind of make sense. Oops. This should kind of make sense because what we're adjusting here is as k gets wider, this blue region creeps out into the edges. But what may not be perfectly obvious to you is the fact that if you start to increase your sample size, this interval is going to actually get smaller, right? So here it is at 100, here it is at 300. You can notice that this interval is getting smaller in size. The other way to make this interval smaller is if you happen to be dealing with a smaller standard deviation. Essentially, your mean is just going to be where the middle of this particular interval falls, so that's not going to affect the size of the interval. But your standard deviation, your n size, and what we'll soon call our confidence level, or the middle percent that we're looking for, will have an effect. So you can use this you can use this function that we made to kind of explore the relationship there. All right. So the last thing I want to say, as we're moving towards confidence intervals, which we'll talk about on Wednesday, this is the important lemma to kind of keep in mind. So if we assume that xi is sampled from a normal distribution with a certain mean and standard deviation, then the probability that your sample mean random variable falls in this interval, so this is essentially the lower bound and the upper bound that we computed using this function, right? Using our margin of error approach. Here's our margin of error. Oops, this should be a plus. Sorry, that should be a plus. Then the probability is 1 minus alpha. Okay, I will often refer to this as the 1 minus alpha, or the k% middle of the sampling distribution x. And this is primarily the result that's going to give us our confidence interval approach when we start talking about this on Wednesday. All right, thanks for listening, guys. Have a good snow day.